So this video is the second half of the predicting products series, and this is on double replacement reactions, which in a lot of ways is much easier than the single replacement reactions as long as you are able to write the compounds for ionic formulas. So if you remember about double replacement reactions, it's really the format of AB plus CD gives you AD plus CB, or where the ions basically switch partners. Remember though, these are always ionic compounds and you always have a cation bounded to an anion. You can't ever have two cations or two anions together. So it's going to look like this. Notice that the anions just switched which cation they were bonded to, or vice versa. This is pretty simple to do as long as you can write the formula for ionic compounds and then balance them. There is just one little twist, and I want to talk about it, but first we need to understand what's really going on in a double replacement reaction. So here's what's really going on. Double replacement reactions occur between aqueous ionic compounds. If you remember from that little tiny bit I said to know about state symbol, this word aqueous is actually extremely important right here. Because what aqueous means the ionic compound is actually dissolved in water. This is also important because if you remember anything about the properties of ionic compounds, when ionic compounds dissolve in water, they do something unusual. And what they do is they dissociate. So if you think of the term associate as come together, dissociate is the opposite, and that means fall apart. When ionic compounds go into water, they actually fall apart into their component ions. So think of the ionic compound sodium chloride. It's the most simple one we have. It's just table salt. If I were to drop this into water, it would actually fall apart into sodium ions all by themselves and chloride ions all by themselves. And they are just floating around. We'd say these are Na plus aqueous and Cl minus aqueous. And that's what's going on. And so because all these free ions are floating around in water, if I combine two ionic compounds together, both of which are aqueous, their ions can reconfigure and join with each other. The thing is though, some ionic compounds are actually not soluble in water. So what that means is if I have ionic compound A and it's soluble in water, and ionic compound B and it's soluble in water, and I mix them together, I might get ionic compound C, which is also soluble, and ionic compound D, which isn't soluble. If that happens, what will occur is that ionic compound D will actually fall out of solution and become a solid called a precipitate. And the precipitate appears because all of a sudden you have these two clear solutions mixed together, and lo and behold, you have a color that falls out. You actually saw this in a lab that you did when you mixed potassium iodide and I believe it was lead nitrate. What ended up happening is the lead iodide fell out of solution as a very bright yellow color. That was the precipitate. So how do we know whether ionic compounds are going to make a precipitate when they come together? Well, we have this chart, and I'm going to show you the chart right now. So this is the solubility chart, or the solubility table. You will need to use this to figure out whether or not a precipitate will form. But this is really kind of the last step you go through, and I'll show you how to do this. But let's practice right now talking about how to solve double replacement problems where you need to predict the products. So here are two practice problems. Let's just take them in order. The first one is silver nitrate and potassium iodide. So all we do is switch partners. I'll draw the arrow and then I'll write the answer below. So this time silver is going to go with chlorine and potassium is going to go with nitrate. And then we need to make sure we get the charges correct. In this case, we know nitrate is -1, so silver, even though it's transition, has to be +1. Chlorine is from the PR table, it's -1. Potassium is +1, so therefore they keep their charges +1 and -1. I don't need any subscripts there. -1 and +1, I don't need any subscripts there. This one is all correct in terms of writing their formulas. If you need practice, please go back and look at your stuff on how to write the formulas for ionic compounds. And the last thing I'm going to do is I'm going to balance the equation. In this case, this equation is already balanced. The really last thing you should do is go and check for state symbols And the way we do that is with our solubility chart. So let me get that out. So when we use our solubility chart, what we're actually looking for is anions. So let's just work at this one. We have chlorine as the anion, and we have NO3. So I'm going to go down my chart. I find Cl, and it says all chlorides, bromides, and iodides are soluble, except silver, lead, and mercury. This is silver chloride, which means it's not soluble, which means this is going to be a precipitate, and it's going to fall out as a solid. Then we go to our other product, it's KNO3. We find NO3 is the anion. It says all nitrates are soluble. This is going to stay soluble in water. It's going to be aqueous. And that's really all there is to it. You will always get this chart. So let's try the second one. We have lead nitrate and we have potassium iodide. They're going to swap. So PB is going to go with I. And K is going to go with NO3. We know this is the same one as above, but let's just show you how I do it again. In this case, nitrate is -1, but I have 2 of them, which means I'm getting a -2, which means lead must be +2. Put the -1 on nitrate. Iodine is from the periodic table, so I know it's -1. K is from the periodic table, I know it's +1, which means to do this right, I actually need to put a 2 down here to solve it. And then let me go ahead and erase all of my math workings. Obviously, you guys could just rewrite the equation where you want to put them. And then finally, the very last step is to check for solubility. So we have I and we have NO3. We know NO3 is the same as before. It's going to be soluble, so this is aqueous. I, we go find I. I is here. It says all chlorides, bromides, and iodides are soluble except AgPb. This is PBI, so it's not soluble. This is going to be the solid. So AgCl and PBI2, these are both going to be what we call precipitates. If you were to put this together in a lab, you would see the solid color fall out of solution. So that's really it for this. I'm going to show you kind of a practice lab. You have a virtual activity next, which lets you practice about 4 or 5 of these equations. But really the hardest thing here is to make sure that you know how to write those ionic compounds correct. As far as figuring out what a precipitate is, that's a nice to know. I may ask you, if given you the chart and gave you a formula, whether or not it's a precipitate. But other than that, there's not a whole lot here you have to do. So practice, 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 and then you'll get better at this.